Once upon a time, Tom and Lily saw things. This is actually a modern autoregressive language model generating text token by token. But that output isn't coming from a modern server farm. It is running locally on an 8-bit microprocessor released in 1975, utilizing exactly 25 kilobytes of available user space RAM. The exact hardware in question is a vintage BBC Micro from the 1980s. The 6502 processor powering this machine carries a severe architectural limitation for anyone trying to run a neural network. Its instruction set does not include hardware multiplication. Taking a modern transformer-era concept and forcing it onto a microprocessor that cannot physically multiply requires us to strip out decades of assumed best practices. By doing so, we isolate exactly what underlying computation is actually required to emulate intelligence. Attention relies on a key-value cache, assigning a unique vector for every token processed. As the transformer generates new tokens, that cache expands linearly, rapidly breaching our hard 32 kilobyte limit. On a vintage microcomputer, this continuous context growth guarantees an immediate out-of-memory failure. To run inference here, we have to abandon attention entirely and pivot to a recurrent architecture like Mamba. Rather than looking back at a growing list of previous tokens, a recurrent model compresses all historical context into a fixed 56-dimensional hidden state vector. Because the state is fixed, the computation has the exact same mathematical shape on every single forward pass. When memory is an absolute boundary, trading the exact recall of attention for a static recurrent state is the only mathematically viable survival strategy. Resolving the memory growth solves the context problem, but we still have to squeeze 52,000 required neural network parameters into our remaining sliver of usable RAM. To achieve this density, we utilize the BitNet architecture to radically compress the model weights. Standard language models store weights as 32-bit floating point numbers. BitNet applies extreme ternary quantization, forcing every single weight into one of three distinct values: -1, 0, or +1. By discarding precision, each parameter now requires a mere 1.58 bits of storage space. This compression lets us pack 4 of these ternary nodes seamlessly into a single 8-bit byte of memory. While packing 5 parameters per byte would technically be more efficient, extracting them on the 6502 processor requires repeated floor divide operations. Since the CPU lacks native division, the computational cost is far too high. At 4 parameters per byte, each value is assigned a neat 2-bit chunk, meaning unpacking the data requires nothing more than a fast right-shift operation. Pushing quantization to this extreme moves the core bottleneck. We no longer worry about raw memory capacity, but rather the speed of unpacking data at the bit level. We still have to account for the CPU's missing instruction set. When a 6502 processor needs to multiply, it fakes it using a repeated bit shift and add sequence. That workaround is incredibly slow. Executing a single 8x8 multiply and accumulate operation drains 150 clock cycles. BitNet's ternary weights bypass this completely. Because every weight is exactly -1, 0, or 1, the matrix multiplication dissolves into simple addition and subtraction. Calculating a dot product no longer requires math. It simply means taking the input value and adding it, subtracting it, or if the weight is 0, skipping it entirely. The 15-cycle penalty collapses into a 30-cycle accumulate operation. If you want to see more teardowns of how modern AI maps onto hardware constraints, take a second to hit subscribe. By removing the need to multiply, we prove that massive flops and complex matrix operations are a hardware-imposed crutch. They are not a mathematical necessity for language inference. Running this simplified math introduces a low-level precision mismatch. The model stores activations in 8-bit, but rapidly accumulating them risks immediate numerical overflow. To prevent the program from crashing, the engine uses a 16-bit accumulator. This safety buffer allows up to 256 terms to safely pool together. The problem hits after the layer completes, when we have to squeeze those 16-bit values back into an 8-bit activation space for the next round. Applying a standard hard clip causes 83% of our accumulated data to pile up at the boundaries, destroying the dynamic range. Instead, a learned per-layer right shift dynamically scales the values before they are clipped, preserving the distribution. When it comes time to generate the final token, standard Softmax sampling requires calculating exponential functions, which the 6502 cannot do. The workaround is a pre-computed lookup table that maps integer offsets directly to probability values. Creating a model that operates entirely on these primitive instructions requires a modern training environment. We use an Apple M-series processor to calculate the initial parameters in full 32-bit floating point precision. The training process utilizes a straight-through-estimator mechanism. This means the forward pass quantizes the weights strictly into our ternary states, but the backward pass still calculates the gradients at full precision. The final export is a highly dense configuration, exactly 13 kilobytes of model weights running on 9 kilobytes of pure C inference code. Offloading the complex gradient math and scaling discovery to a modern GPU during training means the final deployed inference engine runs on pure dumb addition. Looking at a 6502 processor is an exercise in constraint, but scaling this concept up points directly at the future of modern AI infrastructure. The exact same arithmetic simplification that makes inference viable on a 1980s microcomputer is what the BitNet architecture promises for data center scale language models. Our reliance on high-precision matrix multiplication in GPUs is a historical artifact of hardware design. The BBC Micro proves that addition is enough. If coherent autoregressive inference can execute within 25 kilobytes of RAM without multiplication, the theoretical floor for running local AI is vastly lower than standard scaling laws suggest. Right now, we brute force massive parameter counts with raw electrical power, rather than optimizing the underlying arithmetic. Imagine the yield of abandoning generalized compute hardware entirely and printing dedicated silicon explicitly designed for 1.58-bit ternary math. True efficiency requires mechanical sympathy, building software architecture explicitly for the specific physical realities of the hardware it runs on. Building bigger clusters to support bloated math is a brute force approach. Optimization means stripping intelligence down to its absolute barest arithmetic bones. Thanks for watching. I'll see you in the next deep dive.